divide by 337.43. And this is equal to 100 divided by S prime. Okay. Right. And we know S prime has to be smaller because it's taking more shear flow. Why? Because you have higher value of first moment of area, right? So from here, your S prime will be equal to 100 times by 337.43 divided by 700 divided by 39.6768, 1.215. Okay, 1.215. Okay, so you can see, okay, what you can realize that you can see that the spacing at the S prime, okay, is smaller. Why? It's taking a much higher what? It's taking a much higher second moment of first moment of area compared to the smaller part. Okay, so this answer is correct. Now I'd like to do something further. Okay, so still focus on this cross section over here. Let me start on a new page. Okay, and we are now what we're going to do now is we are going to determine the shear stress distribution equation, okay, on the flange and major web. Okay, so how about do we do this? Okay, so we know that over here, this is our geometric centroid. Okay, so this is our geometric centroid. Okay, so given we have our transformation, this is our X, Y, and Z. Okay, so let's consider the flange. So the flange is basically this region over here that I'm highlighting in yellow. Okay. So the distribution equation for this case at the flange will be a function of Z. Okay, because we want to find based on the shear flow, right? Based on the shear flow, relative to the shear flow, how the first moment of area increases from left to right and how it affects our shear flow, right? The bigger the first moment of area, the bigger the shear flow. Okay, so if I'm going to just draw half of this figure. So remember, at this point down here, this is a what? Our junction, right? So the shear flow we design does this, and then it goes to here. So over here, this is known as our flange. So this part, right, is known as our flange. So I'm going to call this our minor web. So the first moment of area at the minor web is a constant. So IE over here, going towards the right, that is our Z. Okay, so this first moment of area will be a function of what? Will be a function of Z. Okay. So how about do we do this? Okay. So Q as a function of Z now. Okay. So the first moment of area of the minor web we know is equal to what? We did calculate. We did calculate the value. So I'll do this. Okay. So Q Z of the minor web plus by Q Z as a function of Z for the flange. Okay. Up to the junction only, because at the junction, the shear flow on the left will meet the shear flow on the right. Okay, and it will hit the same peak value. Okay, so this will be equal. So we know that over here, this value is a constant, right? So the width is equal to 1. The depth is equal to 3. The Y bar is equal to 3.3548 minus by 3/2, right? Then plus the width is going to be Z. Yes or no? So this is going to be the Z, the width will change. The thickness, right? The depth is constant, so the depth is equal to 1. The Y bar is equal to 3.3548 minus by 1 divided by 2. Okay, so this will be equal to 3.3548, 3.3548 minus by 3/2 times 3 times 1. So it's equal to 5.5644 plus by 3.3548 minus 5.5 times 1 is equal to 2.8548 Z. Okay. And then the shear flow of the flange as a function of Z will be equal to, so V, we know V is equal to 700 divided by I, which is equal to 337.43. Thickness is 1 inch, right? And then you have 5.5644 plus by 2.8548 Z. Okay. So this will be equal to 700 divided by 337.43 divided by 1 times by 5.5644 is equal to 11.543, 11.543 plus times by 2.8548, 5.922. Okay. So this is the first moment. This is how the distribution equation looks like. Okay. So now if I'm going to put over here, I'm going to draw slightly lower. Okay. And hold on, before we go any further, we have a limit. The limit over here is where Z is 0, Z to 5 inches. Okay, you don't go beyond 5 inches. So this is our, if you were to sketch this out, this is our Z, This is our shear stress. So we are going to start from 11.543. And then we are going to hit a gradient. And at this point over here, which is equal to 5, this point will be equal to 11.543 plus by 5.922 times by 5. Okay, so 11 or 5.922 times 5 plus by 11.543 is equal to 41.153. Okay, so this is equal to PSI. So when you see this, I'm going to make sure that this is a straight line. Okay. Okay. So that is the distribution profile at the flange. Okay. So the next thing that we're going to do is we are going to consider the shear stress distribution of the web or of the major web. So now we know that at the major web, right? All these are, so this region is a constant, right? So now we know that the distance from here to here, oh, different color. So this will be equal to 3.3548 minus by 1. Okay, 3.3548 or 2.3548. And if you look at the function now it's a function of y, right? Because this is of z. So you're going to form the limits will be from 0 is from the datum, right? And y, and it's going to be up to 2.3548 because the distance from here to here is 3.3548. Let me check. 3.354, correct. Okay. So from here, we are going to find the first moment of area Q. Okay. So we have to, so we have the this part over here, we have the actual value of this section over here, right? And that value we calculate earlier is equal to 39.6768. Okay, 39.6768 plus. Okay, so we know that the width, this width over here is 1.5. The depth is equal to 2.3548 minus y bracket. The y bar is 2.3548 plus by y, okay, multiplied by half. So this will be equal to 39.3768 plus by 2.3548 squared times by 0.5 times by 1.5, 4.1588 minus 1.5 times by 0.5, 0.75 y squared. Okay, so this will be equal to 39.3768 plus by 4.1588 is equal to 45.5356 minus by 0.75 y squared. Okay. Let me check again. 39.3768 plus y 4.1588, 45.535356. Okay. So from here, your shear stress is equal to the V. I can't remember. It's 700 divided by the second moment of area, 337.43. Thickness 1.5, 45.5356 minus by 0.75 y squared. Okay. So from here, this will be equal to 700 divided by 337.43. Okay. Times by 45.5356 is equal to 62976. Okay, let me do it again. 700 times by 45.5356 divided by 337.43 divided by 1.5. 62976. Okay, minus 700 times by 0.75 divided by 337.43 divided by 1.5. 1.037 y squared. Okay, so this is the value, right, of our shear stress distribution. Okay, right, I'm going to stop here. Okay, and as I said, the homework is there, and try out on the homework, and I'll see you guys next week. Okay, bye.